Hey everyone, so we're going to continue our discussion about vertical projectiles, and in particular talk about something called air friction. Now, one thing to keep in mind is that a lot of the problems that we're going to be dealing with free falls tend to be the ideal cases where there's really no air friction. This is important because in the real world, there actually is air friction. And in fact, you do need to know how air friction affects problems. However, you don't need to know how to do it quantitatively. You only need to know how air friction affects a problem qualitatively. For the most part, it's because of the lab aspect. A lot of the problems in the AP questions tend to be kind of almost lab practicals. Why does this happen? And you need to be able to know how air friction affects things, technically. However, you don't actually need to know how it affects it, with numbers and calculate stuff, mainly because that requires calculus, and we don't touch that. But going back, what is air friction? Well, it turns out that objects are all affected by air friction as they fall. This is actually pretty much the reason why, even though we say that all objects fall with the exact same acceleration of 9.8 meters per second squared, it doesn't seem like that. When you drop a bowling ball and a feather, they don't hit the ground at the exact same time. The bowling ball hits first before the feather. Why is that? It's because of air friction. Air friction affects objects differently as they fall, so the feather gets affected more so than the bowling ball. Now, so what does air friction do? What air friction does is it changes the rate at which the velocity increases. As it falls, objects get faster and faster, and air friction decreases that increase in velocity. Another way to put it is that it decreases the acceleration of objects as they fall. Instead of an object falling at 9.8 meters per second squared the entire way down, the acceleration will decrease as it falls, depending on the object. It could be a very quick change, like with the feather, or it could be very slow and gradual. Uh, Now, there are a few things that could affect how strong the air friction is on an object as it falls. The first is the density of the fluid in this particular air. If you have an object falling in something, different type of gas besides air, or in water, let's say, then that density of the fluid will make the air friction greater. The shape of the object also affects the air friction. So you might notice that if you change the way that things look, like a kite or a parachute, that's going to affect how much air friction it experiences. Bullets are shaped a very specific way. Arrows are shaped a very specific way in order to affect and change the air friction that they're experiencing. The other thing is the relative velocity with respect to the air. So, for example, how the object moves and whether or not the wind is moving in the same direction or in the opposite direction. That could also affect the amount of air friction. So, what happens to when an object's being thrown to the ground? What happens to this air friction that's acting on the object? Like I said, when you throw an object down or when an object's falling down, there is an acceleration due to gravity pulling it down. However, there's also going to be a air friction pushing it up, acting in the opposite direction. That's something that we're going to talk about later when we talk about forces. We'll talk about friction and how it always opposes motion. Air friction always opposes the direction that the object is moving in. So if you have an object falling down, the air friction will always end up pushing upward onto an object. And this means that it's going to end up, and as it falls and it gets faster, that force, that air friction going upwards starts to increase. So that means that in the beginning, the object will start going down at 9.8 as there's no air friction. But then as it starts getting faster and faster, that air friction begins increasing. Instead of it being 9.8, it then becomes 8.8. Then it becomes 6.8, then 2.8, and then eventually it'll go all the way up till it reaches zero. At zero, that means that the acceleration pulling it downwards and the air friction pushing it upwards are canceling each other out. So there's no more acceleration. When this happens, when those two accelerations cancel out, we end up having a point called terminal velocity. Terminal velocity is essentially when the object stops speeding up and stops changing its speed. All right, so here are some interesting facts about terminal velocity. For example, one thing to note is that the Empire State Building is just tall enough so that you would end up reaching terminal velocity if you were to fall off the top. In addition, Another interesting note is Felix Baumgartner was actually the first and only person to break the sound barrier without using a vehicle by changing his terminal velocity so that he went faster than sound. How is this? Well, because he was dropping from such a high altitude, the amount of air there, the density of the air is much lower, meaning that he's actually able to increase to a much higher terminal velocity than he would have normally been able to near the surface of the Earth. This allowed him to be able to break the sound barrier and do that without the use of the vehicle, because normally the speed of sound is much higher than the human's terminal velocity. I forgot the exact numbers off the top of my head, but you can ask me in class. Interesting note though, if you actually look at the video that gives you the information about his velocity as he falls, you'll notice that not his velocity does increase uh, to a much higher velocity, breaking the sound barrier. But then once it reaches a certain point, it begins decreasing again as he starts entering into thicker and thicker atmosphere, and the air becomes denser and denser. The air friction starts affecting him again, and all of a sudden he starts slowing down until he actually reaches the normal terminal velocity. So technically, no matter how high you jump from the Empire State Building to where Baumgartner fell, from the edge of space, essentially, all people will end up hitting the ground with the exact same speed. Interesting note. Now, let's talk about how we're actually going to deal with the vertical projectile aspect. In particular, throwing objects up into the air. Now, this one's actually pretty straightforward. If we throw an object up into the air, uh, all that does, besides what we talked about with the it being dropped in the free fall problem, is the fact that we now have an initial velocity to take into account. That's pretty much it, and the fact that that initial velocity is going to be positive. If it's thrown up, it's positive. If it's thrown down, it's going to be a negative initial velocity. That's pretty much it. The way the equation works out doesn't really change. Uh, there are a few things to keep in mind, like for example, they'll talk about the time of flight in the air. So you'll have to know when how long it's in the air, going up and down. One thing to also note is if it's being caught at the same height, that's another piece of information that's telling you that the initial position and the final position are the same. So essentially, you can say that they're both zero. You want to be able to recognize when your projectiles are either symmetric or asymmetric. Uh, the difference being in a symmetric one, we know that everything about it going up is the same about it going down. Asymmetric would be it landing at a higher height or a lower height than what it started. And in that case, you can't make that same claim. So there's a lot of simplicity in a symmetric projectile. But a lot of that you'll see in some of the practice problems. And that's pretty much it. There's nothing else to talk about with vertical projectiles. We'll talk a little bit more about the other types of projectiles later. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.